All right, I guess I will get started. I think Nima, well, is doing something in Maryland. All right, how's everyone doing? Good, there's fewer woohoos than yesterday. Okay, all right, fair enough. All right, well that's good. So obviously this is my last lecture on approaches to the hierarchy problem. So I will try to make it as woohoo as possible. You can decide if it's woohoo or woo-woo. So what I want to talk about today, I want to briefly go back over something that we skipped yesterday, which was talking about the historical sort of anthropic reasoning for the electroweak hierarchy problem, just because that sort of is the canonical example of classes of solutions to the hierarchy problem where we are somehow making use of the existence of multiple possible vacua over which the Higgs mass parameter varies. And the reason why that's a good thing to remind ourselves of is that it's inspiration for some of the very newer solutions to the hierarchy problem that don't necessarily put the solution in many, many different possible universes assembled to a multiverse, but try at least to put all of those vacua into the same universe, which has a lot more experimental prediction. So then I will talk about the relaxion. I'll talk about two different types of relaxion and some of the shortcomings of that picture. I will talk about naturalness. And then I will end with much more speculative comments about directions that it is probably profitable for us to head in the future, in particular to talk a little bit about UV-IR mixing, which is a way to understand systematically why Wilsonian effective field theory might break down for the Higgs. Okay. So again, the sort of third way that we can think about solving the hierarchy problem by drawing these cartoons is the idea that we have some large cutoff associated with the scale of quantum gravity. We have some high cutoff associated with the field theory of the standard model. We have some large parametric hierarchy. But either we have many, many different versions of the story, each of which lives in a different universe. And then we have to explain why we live in a universe where the tuning turns out to be just right. So that's what we normally think of as anthropics. Of course, the challenge of this picture is that it puts the many, many different possible values of the Higgs mass parameter into different universes where we don't have access to them. But other versions of the story might be to put all of these different pictures in the same universe, although separated from each other in well-defined ways. And then the final possibility is just to have one version of the story, but simply to have many, many possible minima within the same theory and have some dynamical process over which the Higgs mass can be selected. So the version where these live in different universes, of course, is anthropics applied to the weak scale. The version where all of these pictures exist in the same universe is what we call unnaturalness, due to Nima and David Pinner and others. And the version where there's really only one version of the Higgs in the hierarchy, but many, many possible minima over which the Higgs mass is dynamically scanned, that, of course, is the idea of the relaxion. Okay. So the normal idea for anthropics comes to us, of course, originally from Weinberg's proposal for explaining the smallness of the cosmological constant. For the cosmological constant, the bound or the argument is very robust. If the cosmological constant is too large, then things spread out too quickly to ever form structure. And if you assume that some form of collapsed structure is necessary for the formation of observers, then you can work out what exactly the bound needs to be on the cosmological constant. And what's satisfying about Weinberg's explanation is that it is relatively insensitive to deformations of the theory, right? Really, there are many things you could try to do to change the details of structure formation, but the bound that you get on the cosmological constant is insensitive to these. And that's why it's a satisfying explanation, because it doesn't really require you to make many assumptions about how the underlying parameters of the theory are formulated. Given the success of that in explaining the cosmological constant through the existence of many, many different universes in which the Cici varies, you might apply the same reasoning to the weak scale. The first thing, of course, you should ask is there a parametric bound that prefers some value of the weak scale related to anthropics? And the argument for that is what's known as the atomic principle. So this is the supposition that even before we wanted to get something interesting like structure, we would want to get something like atoms. And so the argument is as follows. If you imagine in the standard model that you vary the dimensionful parameters, Namely, you vary the Higgs mass squared parameter, but you keep all of the dimensionless parameters fixed. Then you can just think of making an argument where you take all of the known properties of the standard model in nuclear physics, and all you really do is imagine what happens as you change the value of the Higgs vev, right? If we keep everything, all the dimensionless constants fixed, to good approximation, the only thing that varies in this picture is the Higgs vacuum expectation value. And of course, the thing that's most interesting, if you want to care about atoms, is to think about protons and neutrons. Now we know that if we keep the Yukawa couplings fixed, we can work out what is the mass splitting between neutrons and protons. It turns out, of course, it's a function of the contribution to the masses of the quarks that comes from electroweak symmetry breaking and some binding energy piece. And so famously, this tells us that, of course, the neutron is heavier than the proton and will decay into the proton through weak decays. And now you can ask the question what happens as you vary the vacuum expectation value above and below the value that we see in the standard model. Varying below the value you see in the standard model is not very interesting from the perspective of anthropics, right? We don't really, from the perspective of the hierarchy problem, we don't really care if the Higgs vev is much smaller than the value we observe. That really just tells you the hierarchy problem is worse. But you can still ask the question, if you make the vev much smaller, of course, what happens is you flip the hierarchy. The proton becomes unstable to decay into the neutron. But because you're not actually changing nuclear binding energies, it's still possible to create nuclei in which the proton is stabilized by the binding energy. So it's not obvious that something violent and terrible happens. But is there a question?
Can you just quickly explain how you can flip the sign? Because if you would expect it just rescale.
If you make this much, if you make this number.
No, I understand this formula. Yeah, but the question is how you in principle flip the sign. Because you would imagine if you just scale up and down Hawk mass the same way.
What would I? Oh, sorry. What is your concern?
If you just rescale the Higgs vev.
Yes.
Well,
you have a binding energy piece that's independent of the values of the quark masses, and you have a piece that depends on the values of the quark masses, right? And the sum, in particular, of up, and down versus down, down, and up, right? Okay. So the more interesting question is what happens as you make V larger. So this quantity, of course, this quantity just tells you that the neutron-proton mass splitting grows. The quantity that's really interesting is not the mass splitting, but is actually the reaction energy, right, which is this difference minus the mass of the electron. That's what you have to do in order to get, that's what you get by having the neutron decay. And of course, that number is 2.5, just taking out the electron mass. Okay, so the question you want to ask now is, of course, we know in the standard model the neutron is unstable to decay into the proton, but the thing that allows us to form atoms is the fact that in nuclei there's also a binding energy, and the binding energy renders the neutron stable within atoms. Okay, so you can go ahead and work out what are the nuclear binding energies, and how do they actually depend on the Higgs vev. And this argument, of course, is much less precise, but loosely speaking, those binding energies are fixed by pion exchange, and so that means that the dominant contribution, we know for small up and down masses, of course, the pion mass goes like the square root of the weak scale, and so we can work out actually the effect of changing the value of the vacuum expectation value, not only on the reaction energy for neutron decay, but also on the nuclear binding energies. So the details are not really worth going into. The only important thing you have to know is how the pion mass scales, and that gives the parametric contribution to the binding energy. But at the end of the day, with some simple model for how the binding energy should work, a simple parameterization of the binding energy is that it has some constant piece that's independent of the electroweak symmetry breaking scale, and then there's some piece that depends on the vev through the fact that this potential is shaped by the mass of the pion. Okay. So now you just want to ask yourself the question, okay, as I change, so in particular, this is the binding energy just for the deuteron, right? That's really the only case where we can have a simple model to work out how the binding energy parametrically depends on the Higgs vev. And now you can just ask yourself the question, okay, as I increase the vacuum expectation value, there should, of course, be a point at which the reaction energy exceeds the binding energy, and the neutron is no longer stable, contained within the deuteron. All right, so you can go ahead and solve the equation, when does the binding energy equal to the reaction energy? The answer that you get, you hit that equality when V over V standard model is about 1.2. And that's fairly surprising, right? That tells you basically you increase the value of the weak scale by a very small amount relative to the observed value, and immediately deuterons become unstable. And of course, that doesn't tell you that all higher nucleons are unstable, since obviously, as you increase the number of protons and neutrons in a nuclei, the binding energies will change. But because, as we know from nucleosynthesis, pretty much everything interesting starts with deuterons, you might be concerned that this instability really tells you very quickly, as you raise the value of the weak scale, it causes the ability to form complex atomic structures to fail. Okay, so that's the argument, that's the atomic principle. You can relax, you can say I don't care about deuterons, you can care more about more complicated nuclei and atoms, and then the bound becomes something like a few. All right. So the satisfying element of this argument is it does appear to give you, much like the anthropic argument for the cosmological constant, it appears to give you a bound on the weak scale. And so if you had a multiverse over which the value of the weak scale was scanned, you could understand simply by insisting on the existence of atoms why the weak scale takes the tuned value that it does. But the thing that's unsatisfying about this argument, of course, is that we've only allowed ourselves to vary the dimensional properties of the standard model. We've only allowed ourselves to vary the Higgs vev. And it's very easy to imagine that if you allowed other things to vary, for example, if you allowed yourself to vary the values of the up and down Yukawa couplings, then of course you could reverse many of these conclusions, or you could change the parametric scalings. So there is no robust wall in the space of deformations of the standard model where there's an anthropic boundary, and therefore to have a robust anthropic argument, you basically put in as many assumptions as you get out interesting predictions for anthropic bounds on the weak scale. So anthropics is interesting, you can come up with suggestive arguments. As far as I'm aware, there is really nothing that is convincing for the weak scale in the same way that it's convincing for the cosmological constant. And apart from that, of course, this strategy doesn't tell us that we ever get to see any evidence that this is the correct picture of the universe. Is there a question?
Dimensionful parameters, does it make sense to vary on one scale as well, since other dimensions become, and if we made it real small, for example, you might do all kinds of things with atoms.
Yeah, I mean, certainly you could imagine if quantum gravity became strong at atomic scales, that would also be a problem. That's why, I mean, the simplest picture is just to say, let me take the standard model with a fixed cutoff scale and just vary the dimensionful parameter in the standard model within the envelope set by that cutoff. Okay. You can also, of course, there's a very cheeky paper by Roni Harnick and Graham Cribbs and Gilad Perez, where they actually asked the question, could you imagine starting with the standard model, but really breaking getting rid of SU2 so that the only actual symmetries of the theory were QCD and electromagnetism, and could you actually construct a theory that looked like the standard model, had all of the interesting properties of nuclear physics and astrophysics, you could get extended structures, but never have had a weak group and therefore never have had a light Higgs. And it's very hard to know if their arguments are correct because as you start to extrapolate what happens in nuclear physics and astrophysics when you drastically change the properties of the standard model, it gets very hard to know what's going on. But they've at least heuristically argued that it's perfectly possible to construct a weakless universe where there is no elementary Higgs and there was never a weak group that persisted to low energies. And that would also tell you there's certainly some direction in the space of deformations of the standard model where these anthropic bounds don't apply. Okay. Yes?
I see the argument, so what? What if the universe was not like this?
It has the character, yeah, no, I mean, I also do not find it a satisfying explanation, but it is possible to find it a satisfying explanation. And it is also possible that this is in fact how the universe works, and the universe doesn't care whether we're satisfied, right?
There is no dynamical reason
In this picture, there's no dynamic. I mean, you can construct potentials that give you some multiverse where the only thing that is varying in some local neighborhood are the dimensional parameters. So it is possible to argue, it's possible to construct theories in which this assumption is a justified one, but there is no guarantee that this is how, a landscape of vacua should look.
Ask the same question about, say, fine structure constant. If fine structure instead of 1/157 was 1/2, the universe would have been totally different.
Absolutely, absolutely. So I think the argument that people who are pro-anthropic would make is that what we see with the atomic principle is that a small deformation of the standard model leads quickly to some anthropic boundary, whereas things like the weakless universe require something that is a very large excursion in parameter space. But I don't know. I don't know what the measure is on these deformations of the standard model, so I don't know if I should be satisfied. I really actually don't want to spend too much more time talking about anthropic, so if there are more questions, we can reserve them for the discussion section. But this should be inspiration to you. So the things that are unsatisfying is that you only get out what you put in, and it's also, you're not guaranteed in this picture to ever have any observables associated with this explanation for the lightness of the Higgs. So it is possible, of course, because this picture requires you to believe in a multiverse, that there were vacuum transitions in the very early universe between different minima, and it could be that there is some residual effect of that, some residual evidence for bubble collisions in the early universe. But to see that sort of thing, especially with inflationary early conditions for the early universe, you had to get very lucky. Okay, so if this is what's going on, it is in principle possible to find evidence, but certainly no one promises it to you. Okay. So the first thing you might try to do, though, to take as inspiration, if the game is to imagine allowing the Higgs mass parameter to vary across many different possible vacua, what you might instead want to do in order to get interesting predictions and observables is put all of those possible different minima into the same universe. All right, so to imagine that instead somehow in our universe, many different values of the Higgs mass are somehow accessible, and then to come up with a mechanism that instead of through fine-tuning picks out the value that we see, picks it out through some dynamical process. So the two examples of this, one is 2 years old, one is 1 year old. So you can tell this is a very fertile new territory for development. So the first, of course, is the relaxion, and the second is naturalness. So let's start with the relaxion. So the relaxion, some version of the relaxion is probably an idea that you've had ever since you first learned about the hierarchy problem, or ever since you first learned about axions and how axions work. So as you've learned from Michael, of course, the beauty of the axion is that it takes the theta angle in QCD and it introduces a field where at the minimum of that field's potential, the total contribution to the strong CP angle from the bare term plus the expectation value of this field is 0. Okay, so now you can ask yourself the question, can I do that same thing for the Higgs mass, right? So could I imagine having some large value of the Higgs mass squared parameter that is proportional to some cutoff? So here capital M, we will imagine is some large value that's of whatever order the cutoff scale is of the Higgs sector. So that's some bare piece, plus we couple, in this case, it will be through a super renormalizable interaction, so a dimensionful parameter G. We couple some field phi to the mod squared of the Higgs doublet. Okay, so now you can look at this, right, and you can say, great, what I think of as the entire contribution to the Higgs doublet mass parameter is the sum of whatever this bare term is, which is naturally the size of the cutoff, plus the expectation value of some field. And now the question is, can I arrange for the minimum of the potential for this field to be at the place where the sum of these contributions is 0, right? That would be an axion-inspired explanation for the lightness of the Higgs mass. Now the problem is, of course, as we already understand very clearly, nothing is special about the Higgs mass squared being 0. That is the entire issue, the lack of technical naturalness, that has made the hierarchy problem such a hard problem to solve. The innovation that makes this work, which is due to Peter Graham, who will be here next week, and Sujit Rajendran and David E. Kaplan, is to note that there is one thing that is somewhat special that happens when the Higgs mass parameter goes through 0, or at least when it goes from very positive values to very negative values. So of course, by the way, so the picture that they have is you start with this sort of combination of things. You imagine that this field phi has some shift symmetry. That shift symmetry is broken by this dimensionful parameter G. okay? But you imagine apart from G, that's the only source of breaking of the shift symmetry. Otherwise, it has an exact shift symmetry. That means, of course, we should write down a generic potential involving all possible powers of G and phi, not just the leading piece, but also things involving higher powers of G. For our purposes, the most interesting pieces would be things like G squared phi squared, and all higher terms will not be particularly relevant for us. Okay. There are many subtleties and caveats associated with this. So I think the authors of the relaxion would say that the parameter G is a technically natural parameter because when it is taken to 0, there is a manifest shift symmetry of the field phi. That is something of an abuse of the notion of technical naturalness for reasons that we'll get to in a few minutes. So I would say this parameter is not technically natural, but it is a dimensionful parameter. It's super renormalizable. Okay. So in addition to a potential for phi that breaks its shift symmetry plus a coupling to the Higgs, the one other thing they want to imagine is that this particle is like a QCD axion. And I will emphasize, again, the word like because that turns out to be important. But it's like in the sense that it has a coupling to GG dual in the normal axion-like fashion. And so the observation of the original authors of the relaxion is something interesting does happen if you imagine that this field is scanning through various values on its vacuum manifold, or excuse me, if it's just scanning through various values of the field, so it's causing you to scan the values of the Higgs mass squared. If you're scanning the values of the Higgs mass squared from very large positive values going through 0 to very negative values, what happens is you cross through 0, of course, as the mass squared goes negative, the Higgs accumulates a vacuum expectation value. We know when the Higgs gets a vacuum expectation value, then of course it turns on masses for the quarks in the Standard Model. And we know that quark masses, of course, give a contribution to the potential of the axion after QCD confines, right? So normally, if we had no light flavor quarks in the Standard Model, then QCD confinement would still generate potentially a potential for this field phi, but the size of the barriers of that potential are enhanced by the explicit symmetry breaking coming from quark masses. So the point of the authors of the initial relaxion is there are really two interesting contributions to the potential of phi. There's whatever potential, this leading piece in the potential that gives it some slope. And then, as it evolves along that slope, when it turns the Higgs mass squared from very positive to very negative, quark masses turn on. Those quark masses then enhance the height of the cosine barriers that are coming from QCD. They give you wiggles that will actually grow as the VEV gets larger and larger. And so the total combined potential you should think of for this relaxion is some smooth falling potential given by the shift symmetry breaking terms. And then when the Higgs mass squared crosses through 0, you start to pick up larger and larger oscillations, which, at least over some regime of validity, grow with the value of phi, and therefore the negativeness of the Higgs mass squared parameter. And so then the picture that you'd like to have is this, the growth of the barrier starts to turn on right around the Higgs mass squared going through 0. And so you'd like to imagine if you start from over here and you're evolving down this potential, when you start to hit these growing barriers, you stop, and you therefore stop someplace that's close to the Higgs mass squared being equal to 0. Yes?
So we saw in Michael's lectures that when we don't have when we have massless fermions, we can actually redefine fields and get rid of theta terms.
Yeah, so it's a more, okay. There's, absolutely, I don't want to, for our purposes, it doesn't matter what the origin actually of this axion-like coupling is for this field, okay? In particular, this is not even an actual axion-like field for reasons that I'm about to discuss. So the only thing that really matters for us is if we have quarks, light quarks relative to the confinement scale, those give us a contribution to the QCD-induced barriers, potential barriers for this field, okay? And in particular, you know, of course, parametrically what happens is after QCD confines, this gives us a cosine potential that goes like cosine phi over f. And the height of these barriers, right, the height of the barriers should go linearly in the vacuum expectation value, because at least parametrically speaking, this potential goes like the square of the pion decay constant times the square of the pion mass. And we know that the square of the pion mass, of course, goes linearly in the quark masses. And so this is an object that, loosely speaking, goes like f pi cubed times the Higgs VEV times the Yukawa coupling. So at least in some range of validity, this is the picture we should have as we start to turn on quark masses. There should be some height for these oscillatory barriers that is growing linearly in V. All right. So there's lots of caveats to this picture, right? So the first caveat is if we imagine that the field starts up here in its potential and it's undergoing some classical rolling along its potential, then of course there's a large amount of kinetic energy stored in its kinetic terms. And generically speaking, over some large scale of evolution, when it hits these bumps are very small compared to the overall scales of the potential, and that means that in general it will simply roll over all of these bumps. So to actually imagine that you stop when you hit the bumps, you need a source of dissipation, and the source of dissipation introduced by the original relaxion authors was inflation, right? So if I imagine there is an additional field that is inflating while this field phi is evolving through its potential, then that of course provides a friction term for phi and allows us to understand why we've dissipated its kinetic energy. Okay. So the ingredients we need some field phi that's coupling like an axion. We need to break the shift symmetry of this field in some explicit way, and we need it to be evolving along its potential during some inflationary period. And now, of course, we have to work out all the details, how exactly these pieces have to fit together for us to get a mechanism that works in a satisfying fashion. What about the new mass scales like G? Well, so right now we don't necessarily know what G is, but we could imagine G is very small. And then it's just a matter of asking to get some interesting solution to explain why we stop close to the Higgs mass squared being 0, we can figure out what G has to be. So in particular, if you just take this simple classical picture, right, you can ask yourself the question, okay, where exactly am I going to stop? Or what is the value of G for which I stop? And loosely speaking, right, if you just eyeball this picture and you ignore any large kinetic energy stored in the field, you're going to stop at a place where the slope associated or the height associated with these bumps is beating the slope associated with coming down from your shift symmetry. And so that just amounts to the statement, when those two are about equal, right, that's the statement that G times m squared is something that's of order y v f pi cubed over f, right? And so now you can work out the actual size of this parameter relative to whatever the implicit value of the cutoff is, the scale capital M, the scale, the PQ scale, the axion decay constant scale that's suppressing this coupling to GG dual, and what we can think of as just the value of the weak scale, which is where we want to end up, and the pion decay constant, which we know. Okay. So at the end of the day, it will turn out in this simple scenario, the best thing you can do is get the value of this cutoff up to about 10 to the 7 GeV. And to make this solution as natural as possible, to push the cutoff as high as possible, you'll want to make the axion decay constant as low as possible. So if it's a QCD axion, the lowest natural value we can take for it is 10 to the 9 GeV. And for those values, then what we see is G over M turns out to be 10 to the minus 30. Yikes. Okay. And that means, given that M in this case, for the best case scenario, is about 10 to the 7, then that means G is about 10 to the minus 23 GeV. Yeah.
Why does that condition depend on the source of friction? Like, I would have thought that we're...
Oh, yeah. This is just a very naive classical estimate, which turns out to be parametrically correct. Right.
Okay. I mean, I would have thought that we're, like, when it stops, or if it stops, it's all dependent on how...
Yeah, so I mean, the original relaxion analysis, right, is just a series of twiddles. In reality, all of the things are correlated, and really all you should be doing is solving the coupled equations of motion for all of these fields. Okay, but it turns out that parametrically the answer is about right. Yes?
Just understand how this machine works. Now, let's say I set it up the right big scale by doing these scenarios. Then I just calculate the loop correctness of Higgs mass. And let's see if I imagine the new physics at 10 to the 9 GeV, and top loop will give rise to the direct half. Yeah, how does this?
Well, if this is all that happens in this theory, right? So if this is, are you concerned about the contributions coming from this coupling?
Or after this thing was happened, right? Now if I just calculate the top loop correctness.
But what do you mean by after? So what you imagine, what you've done is you defined your potential for your theory, the renormalized potential for your theory. You computed all the loops, right? Okay, that does mean there are some things that we should think of as radiative corrections to this picture, but all of those are just living in this. This is just the statement that there were no, the natural size, including all radiative corrections of the Higgs mass parameter, is of order the cutoff, right? So that's already in here, and we're assuming that it's large. And all we're actually imagining is we have a large quantity, and then we're stopping a field in a place where it largely cancels off this parameter, okay? There's no extra radiative problems induced by this coupling, right? Because this coupling, it's a super normalizable interaction, and it's 10 to the minus 23 GeV, right? Okay, so loops from that are very, very small. All right. Okay, so now you can ask yourself lots of different questions. There are constraints on the field range over which this field has to move. There are constraints on the size of Hubble during inflation. Hubble has to provide enough friction for the field to stop. But also there has to be, while this field is evolving with whatever its low speed is, inflation has to be happening the entire time. And so given some field range for the field, inflation has to last some amount of time in order to always be there to dissipate energy. So you can work out the constraints on this picture. The first thing that you have to worry about is, so the first constraint is, for this really to be natural, we should imagine that we scan over all possible values of the Higgs mass squared, from the value of the cutoff squared on the positive side to the negative side. So to do that, that means the field phi has to evolve over some field range that's of order m squared over g, right? So again, at least keeping in the back of your mind what I'm going to claim are the best case scenario for this picture, where m is of the order 10 to the 7 GeV, so that's 10 to the 14 GeV squared divided by 10 to the minus 23 GeV, right? This is some vast, vast field range. It is vastly transplanckian by many orders of magnitude, certainly far beyond the value of the cutoff. And that's the first thing, of course, that should concern you, that you require the field, this description of the theory to be valid over field ranges that are far larger than any we encounter in a consistent field theory coupled to gravity, right? Modulo efforts to improve the situation with things like clockwork, we don't actually have any really good mechanisms for protecting potentials over transplanckian distances. Generically, there are gravitational effects, gravitational instantons that spoil any perturbative expectations you might have. So the first thing that should concern you is it's very hard to actually understand why you're able to describe your theory in this way over such a large range of field values. But given that this is the field range over which you have to scan, now you can also answer the question, how much inflation do you need, right? So this is the field range over which you have to scan. Now, if this is happening during inflation, you can simply relate that to the velocity of the field and the amount of time over which you're rolling, okay? And then you can work out, because this field is slow rolling in addition to the inflaton, you can work out parametrically what that implies. And so in terms of the parameters of the potential, that actually is the number of e-folds times this parameter g times this large value of the cutoff squared over Hubble squared of inflation. So from that, now you can solve for the number of e-folds. So the number of e-folds of inflation has to be greater than the Hubble scale squared during this process divided by g squared. And right now, it's not obvious that that's a problem. We don't necessarily know what Hubble has to be, but we do know the number of e-folds already is going to be very large, because anytime we're dividing by g or g squared, keep in mind we're dividing by some quantity that is very, very small, and so therefore it's going to be some very large number. Okay, so you already know there'll be some huge number of e-folds. There are other constraints. So as this field phi is going over its potential, of course, if it's going over that field range, the change in the vacuum energy over this field range is of order the cutoff to the fourth. So in order for inflation to be dominating the cosmological dynamics, the vacuum energy during inflation has to exceed the change in vacuum energy due to phi rolling down its potential. All right, so that amounts to a constraint that the Hubble scale has to be greater than the cutoff squared over the Planck scale. This starts to give you, of course, an expectation of what the size of Hubble will be. In addition to that, for this picture to work, what we need is that our classical expectation of classical rolling is winning. Of course, we know during an inflationary epoch, all fields, the fluctuations of fields during an inflationary epoch get quantum fluctuations due to Hubble, and those quantum fluctuations kick them up and down, right? This is the same thing that gives us density perturbations during inflation. And so what we need to be true is that the classical rolling of the relaxion down its potential beats the quantum jumps. And we need that to be true in order to get far enough down the potential. All right. So classical beating quantum gives us an extra constraint. That constraint turns out to be that the Hubble scale is less than this parameter g times the cutoff squared to the third power. Okay, so now you've bounded Hubble from above and from below in terms of the cutoff, and now you have enough conditions to consistently work out what is the parameter space in which this theory works. Okay. There's a further constraint, of course, that you can ask for. You should require that the Hubble scale be smaller than lambda QCD, because, of course, you also need the excitations due to Hubble not to push you over the barriers. You really want to stop, even though inflation is still happening. Okay, but that condition is trivially satisfied once you satisfy these other conditions. Okay, so you can put all these things together, all these constraints together. You already have an expectation that there's going to be some enormous amount of inflation, some large number of e-folds. You have an expectation that the Hubble scale is going to be very small because it's proportional to the third power of this small parameter g. And so when you put the ingredients together, you can find a maximum value of the cutoff that's consistent with satisfying all of these constraints. And that maximum value of the cutoff is about 10 to the 7 GeV, taking f to be the smallest value it can take. But you're not very sensitive to this. It only goes like the 6th power. So what that tells you is you can imagine pushing the cutoff of the standard model up to something that's of the order of 10,000 TeV. So the starting value of the parameters in this potential could be of the size of that cutoff. And then given a starting point out there, your evolution along this potential could cause you to stop where the eventual sum of contributions is closer to the weak scale. All right. So this doesn't get you all the way up to the Planck scale, but it appears to give you something interesting. And that is the nature of the proposed relaxion solution to the hierarchy problem. Now, there are lots and lots of other things that should give you pause when you work out the details. So once you've picked out the maximum value of the cutoff, you can go back through all these parametrics and figure out what are the number of e-foldings of inflation and what is the Hubble scale. So the number of e-foldings of inflation, consistent with this bound, is at least 10 to the 40. All right, so normally we're used to thinking of number of e-foldings that are things like 50 or 60, right? So now you're talking about something that is 10 to the 40. That just means there's an enormous amount of inflation. You're inflating for as long as the age of the visible universe. And the Hubble scale associated with this is very low. It's less than about an MeV. Okay. So this is a challenge to construct an inflationary scenario where these conditions are satisfied. It's not obvious that it's impossible, but it is something that you need to work out in order to believe that this is happening. There are two other things that should give you a little bit of pause when you think about the scenario. So one of them, as I mentioned at the beginning, is a notion of technical naturalness and a notion of where the shift symmetry comes from. Okay. So we said that we imagine this field phi has a shift symmetry, and we imagine that it's broken by this parameter g. Now, anytime, so normally, of course, we would say, great, I know a natural way to get a field with a shift symmetry. Phi could be a Goldstone boson of a spontaneously broken global symmetry, a compact global symmetry. And then I could have a way to understand why it had a shift symmetry that was good over some field range. But there's a problem, which is that, of course, anytime we actually have a Goldstone boson with a shift symmetry that's coming from a spontaneously broken global symmetry, in addition to the shift symmetry, it also has a gauge symmetry under which we shift the field by integer values of 2 pi times its axion decay constant. And the reason for that, well, the reason for that is very simple. There are deep reasons, but the very silly phenomenological reason you can think of is just think about a U1 global symmetry that had some field phi, right? So if we write this, if it gets a vacuum expectation value, and so if we write it in terms of some radial mode times some Goldstone field, right, it's obvious that because of the nonlinear parametrization that we've used to construct the Goldstone field, that if I shift this thing by integer values of 2 pi f, then of course I will return phi back to itself. And so it's simply impossible the theory is, just by construction, the identification of the field is necessarily invariant under these shifts by integer powers of 2 pi f. Okay. So that is the discrete gauge symmetry that lives in any Goldstone that has a continuous shift symmetry that came from a spontaneously broken compact global symmetry. And any theory that you write down that starts with this global symmetry and then breaks it in some way, even explicit breaking, is always a function of the field phi. And so any local quantum field theory will still preserve that discrete gauge symmetry even if it breaks the shift symmetry. Whereas this breaking of a shift symmetry, this would break both the actual global shift symmetry and the discrete gauge symmetry. Okay, so there are two possibilities. One is you started with some compact global symmetry, but there were some non-local field theory effects that broke it, which it's hard to understand how that would work. The other possibility is that this field didn't actually come from some compact global symmetry. Okay. So there are issues really associated with the smoothness of the potential for phi and its technical naturalness. So that's one thing that could give you pause. It's not obvious that this actually satisfies our nominal notions of technical naturalness. And the reason why you would worry about that even more is because this field has to evolve over some enormous range of values, trans-Planckian range of values. We can't understand it as being protected by some compact global symmetry. All right. The other issue you might worry about is the cosmological constant. So if we have a symmetry solution to the hierarchy problem, we can basically factorize what solves the Cici problem from what solves the hierarchy problem, right? We could have a symmetry or technicolor solving the hierarchy problem, and we could have anthropic solving the Cici problem, and that solving the hierarchy problem wouldn't increase or alter the amount of fine-tuning or the number of vacua we had to scan over to anthropically explain the Cici. But in this scenario, right, you have a situation where the relaxon field is evolving, and from minimum to minimum, the change in the bottom, the value of the minimum from minimum to minimum around the weak scale is of order lambda QCD. So that means as you go from minimum to minimum, the value of the Cici is changing of order lambda QCD. But the value of the Higgs mass that's actually changing from minimum to adjacent minimum is much smaller than that. It's knocked down by a factor of g. So what that means is there are many, many, many different bumps in this potential where the Higgs mass squared comes out near the weak scale. But each one of them has a vastly different value of the cosmological constant, at least in units of the cosmological constant. So if you're going to use anthropics and some counting of number of vacua to explain the Cici, now you need to increase or multiply the number of vacua over which you can scan the Cici by the number of different minima over which you could get the Higgs mass right, and that would seem to at least increase the fine-tuning that's required to get the Cici right. All right. This is not a really detailed statement. We don't really have a detailed notion of the measure of vacua that you would scan to get the Cici right, but it's one other thing you should worry about. It's a new problem you encounter if you use dynamical vacuum selection as opposed to symmetries to pick out the value of the weak scale. Okay, there's a final problem. So those are all things that are concerns. Those are things that need to be worked on. They don't obscure the brilliance of the idea, right? The reason why it's worth talking about the relaxion, even a part of these challenges, is it is such an innovative and interesting way of attacking the hierarchy problem relative to what we've been doing in the past, that it's a real invitation to all of us to take seriously what we can learn from it. Okay. But even if you set aside these challenges, even if you solve them, the last problem you have in the simple model is that if this thing is really coupling to QCD, of course, it's giving us a value of the strong CP angle. If I just had the cosine piece, and this thing had settled at the minimum of the cosine potential, then of course we know from Michael's lectures that that would set theta equal to 0. But the minimum now of each of these bumps is not at the minimum of the cosine potential. It's shifted by an amount that depends on, of course, this extra slope that we've superimposed the cosine potential on. So that means the field, the relaxon field, when it stops in one of these minima, relative to theta is equal to 0, it has an order 1 value. All right. So this simple picture, you're trying to use the dynamics of QCD to help you. But in the actual minima in which you stop, you're now predicting a large value for the theta angle, and of course you're ruled out by bounds on the neutron EDM. Okay. So the simplest example works beautifully, is ruled out by a completely unrelated physical observable. Now you can imagine doing lots of different things to deform this picture. So the simplest thing you can imagine doing is repeating the whole story, but not with a QCD-like non-compact axion, but instead with a non-compact axion of somebody else's QCD, for which we don't have good bounds coming from the neutron EDM. And then you can repeat this whole story. There's some details you have to work out. Of course, you still want these bumps to be related to the turn-on of the Higgs VEV, so that other copy of QCD has to have fermions that are charged into that other copy of QCD, but also charged into the electroweak interactions. And then you have something that ties the height of that barrier to the value of the weak scale. So that's something that we call the QCD prime relaxion. It's another very interesting model. It predicts lots of interesting new fermions with electroweak quantum numbers close to the weak scale. And it's just another example of, as you push this picture around, you can get lots of interesting new physics and new predictions that are very different from our conventional solutions to the hierarchy problem. Okay. I think that's all I want to say about the relaxion. Any questions? Yes?
So, is there any way you can possibly play with the bound on the range of phi? So, in some way think, let's say phi is already close to the value at which the mass squared is close to 0. And would that introduce a fine-tuning problem?
So in the simplest picture, it would, right? Just because that would be a non-generic set of initial conditions, and you would be passing the tuning of the weak scale into the non-genericity of the initial conditions. But you could imagine related mechanisms that are scanning the value of a field where there's something special about starting at the origin of field space. So there are relaxion-like proposals that involve moving around the minimum of some thermal effective potential, and those don't necessarily suffer from the need to move it over the same range of fields in order to have a generic solution. Okay. But in the simplest thing, that's to avoid transferring the fine-tuning to the initial conditions. Okay.
Does changing G to G prime change your limits on M, G over M?
Yeah, they change by modest amounts. They don't change. So the things that change, of course, is the pion decay constant of the QCD prime can be different. The axion decay constant can be different, so that gives you some extra parametric freedom. You might think that that could allow you to actually push the cutoff to be arbitrarily high. Then the details turn out to be a little intricate. Let's see how much time we want to spend on it. So I don't want to spend too much time on it, but the basic bounds are as follows. Okay. So to get this to work in a QCD prime, let's imagine you introduce a vector-like lepton doublet, so L and L bar, and a vector-like right-handed neutrino, so N and N bar. Okay. So those things you give vector-like masses, but you also charge them under the electroweak interactions, and you charge them, of course, under that QCD prime. Now, what you need is you need one of those fermions to be light with respect to the confinement scale. So let's make the N's light. And so you can, for range, for a simple seesaw where the L's are heavy and the N's are light, they're getting contributions both from electroweak symmetry breaking and from their vector-like mass terms. Okay. So you make the N the thing that's actually contributing to the axion potential, and you might hope that you could take L to be arbitrarily heavy. Now you have various constraints in play. So one of the constraints in play is that whatever the mass is of the L, because it couples to the Higgs and the N, there is another source of chiral symmetry breaking that contributes to the mass of the N. So that bounds actually how separate you can make the mass of the N from the mass of the L. What are the other bounds you have to have? There are other bounds that you have to have that correspond to the wiggles coming from electroweak symmetry breaking or beating the wiggles just coming from confinement in that copy of QCD. So that gives you another bound that relates the mass scale of N to the mass scale of the pion decay constant. And when you put all those ingredients together, that tells you that F pi has to be close to the weak scale itself, so it can be higher than lambda QCD, but not much higher than V. And it tells you that the vector-like mass of the L can't be much higher than about 4 pi times the weak scale. So once you put those ingredients together of getting all the bumps to work out, you can't arbitrarily separate things. And that's what's interesting, right? It tells you that even though you've changed the parametrics of the setup, you've freed yourself from the standard model predictions, you still require yourself to be somewhat close to the weak scale. Yes?
Is there any way to deal with the large field excursion problem like compactness?
No, so that's, in fact, that's, I mean, so let's imagine, so I'm making this complaint about the fact that this coupling doesn't appear to be coming from some explicit breaking of some global symmetry. But you could also just ask yourself the question, well, maybe I'm being silly by writing this down. Maybe this is just actually the leading term in some Taylor expansion of some set of explicit breaking terms that I would actually get from explicitly breaking a compact global symmetry. Okay. But so what happens then? So what happens then, right, is now you want to imagine phi is an actual axion. It's an actual Goldstone of a spontaneously broken global symmetry. And there's some explicit breaking terms that the smallest piece of which looks like this explicit breaking, but they organize themselves in another way that preserves the discrete shift symmetry. But now what has to happen is you still need to go over that enormous field range, so you still need to go over m squared over g, but m squared over g has to be less than f, right? Because f, if you go larger than f, now the compactness tells you that you haven't gone that far in field space. You haven't scanned over this many values of the Higgs mass because of the compactness. So now you have an extra constraint on F and M, and now if you put in all the other constraints in the scenario, what that actually tells you is M is the weak scale, right? So you would hope to alleviate these problems by making the field compact, but if it's compact, then you're not really scanning the Higgs mass very far, and the actual cutoff of the theory is close to the weak scale. There are ways to try to get around this where instead of having it be one compact field, this is actually some effective field that you assemble by stringing together various different axions, for example, with incommensurate decay constants or with some sort of other mechanism. These are, for example, biaxion theories, triaxion theories, or clockwork theories. It's still not obvious that they actually work in a way that we need them to work, but there are people thinking about whether this can be improved. Okay. I just want to briefly remark, so this is the original relaxion picture. It is a truly beautiful innovation relative to what people have been thinking about the hierarchy problem before. It has some challenges. The challenges are interesting challenges to you to try to address. But you could try to also use it as inspiration to come up with related types of mechanisms. In particular, the ingredients that we needed here is we had some source of bumps, right? And we had some source of dissipation. And what we did was we imagined the dissipation was always there, and the bumps turned on when you took the Higgs mass squared through 0. But we could imagine running the story in a different way. We could instead imagine having the bumps always be there, and instead turning on the dissipation when the Higgs mass squared passed through 0. Okay? So that would be a different way of getting the same outcome. Because in that theory, right, what you would imagine is you could have some bumps that were superimposed over some linearly falling potential, and then right around where the Higgs mass squared is equal to 0, dissipation turns on. So in that picture, if the relaxion is rolling down these bumps, it has enough kinetic energy up here, there's no dissipation, it doesn't really see these speed bumps, it rolls right over them. But then when the dissipation turns on, very quickly it drains the kinetic energy, and it can no longer roll over the bumps. So it still stops close to the Higgs mass squared being equal to 0, but it's for the opposite reason as in the original relaxion model. Okay. So you can ask how you could go ahead and do something of that form. And the natural answer for that is particle production. So the idea behind the particle production relaxion is to take a very similar setup to the original relaxion, so to still have a large Higgs mass squared, to still have some relaxion field that is scanning the Higgs mass squared. There's still some potential for this relaxion. We imagine that it gets a potential from QCD confinement that is, well, not our QCD confinement, but some other confining group that is always turned on. So it just has some cosine potential. And then finally, we imagine, for example, it couples additionally in an axion-like way to some gauge fields. Okay. So I don't want to get into the details of how this works in the standard model, but let me just present you a simple toy model so you can see how the mechanism works. In the simple toy model, we imagine this is some abelian gauge field, and the abelian gauge field is Higgs by a vacuum expectation value for this Higgs field. Okay. Obviously, in the standard model, this has to be some more complicated combination of electroweak gauge fields, but in the simplest version, let's just imagine this is a U1 gauge field, and our Higgs is charged under it. Okay. So what happens in this picture? All right, so in this picture, you have phi evolving along its potential, all right? In general, instead of starting at large and positive values of the Higgs mass squared and going to large negative values of the Higgs mass squared, you imagine starting in the opposite, starting at large negative values of the Higgs mass squared and going to large positive values of the Higgs mass squared. So when you start up here, large negative values of the Higgs mass squared, Higgs has a big VEV. These gauge fields are very massive. As you start to evolve down this potential, the VEV is getting smaller and smaller, the gauge fields are getting lighter and lighter, and eventually you get to a point where for a fixed kinetic energy of this field phi, the kinetic energy of the field phi is such that, and the mass of the gauge bosons is small enough that you can actually have particle production where the energy of the phi is drained into production of these gauge fields. Okay. So you can work out the details. You can just go ahead and look at the classical equations of motion for the transverse fluctuations of the gauge bosons to see the effect. But basically, once the kinetic energy exceeds the geometric mean of this decay constant and the mass of the gauge bosons, you can have efficient production of the transverse modes of the gauge bosons, and that is a source of friction that very quickly drains kinetic energy from phi. Okay. So that's the picture now that you should have. The bumps are always there, but the dissipation, the particle production of these gauge fields, turns on when the mass of the gauge fields gets small enough. So that would be a sort of interesting, clever, different way of doing the same thing as the original relaxion, and this is what we call the particle production relaxion. This is due to Anson Hook and Gustavo Marcus Tavares. So Anson, of course, was a postdoc here at IAS until a few years ago. All right, so that's just to give you a sense, a flavor in which there are many other ways to use this set of ideas constructively to try to solve the hierarchy problem. It is far from clear that we've exhausted all of these different mechanisms, and it's an invitation to you to keep thinking about how you could put these things to work. Okay. So in the last 30 minutes, 35 minutes or so that remain, I want to talk about two more ideas. One is naturalness, which is the most recent way of thinking about trying to use multiple different copies of the standard model to explain the lightness of the Higgs. And then when we finish with that, I want to end with some more radical thoughts about UV-IR mixing. Okay. So what happened in the relaxion is we imagined we really had one Higgs field and many, many different minima in some potential over which the value scanned, and some dynamical reason why we stopped in a value that was close to the weak scale. But the other thing you could imagine doing is having many, many different copies of the standard model, not in different universes that are causally separated from each other, but actually all living together in the same universe, all right? And in each one of them, there's some statistical distribution of Higgs masses just coming from various UV contributions, which means that the value of the Higgs mass squared as you go from standard model copy to standard model copy, of course, will vary just statistically as you add and subtract all these different UV contributions. So the picture you should have is maybe you live in a universe, maybe you could imagine an extra dimension with lots of parallel branes. Each one of these parallel branes contains a copy of the standard model. You could imagine varying the dimensionless parameters in each of these copies, but for simplicity, we can keep them fixed. It's not a necessary assumption. And you can also imagine then that just because of random UV contributions, the Higgs mass squared parameter varies from copy to copy. And the Higgs mass squared parameter should vary from copy to copy. Loosely speaking, statistically, okay, it depends on the probabilistic distribution, but the values of the Higgs mass squared should vary anywhere from negative, whatever the cutoff of the Higgs sector is on these copies of the standard model, to positive, all right? And in particular, that means that there should be some values of the Higgs mass squared on one of these copies of the standard model where the Higgs mass squared parameter is close to 0, all right? And that's just a statement, that's just statistics, right? That's just a statement if I have lots of different copies of the standard model, there are many, many different UV contributions. If I have enough of them, there should be one copy of the standard model where the Higgs mass squared is small enough. It's of order the cutoff squared over whatever the number of copies of the standard model is. Okay, some of these copies of the standard model just live out on the tails of the distribution where the mass squared is close to 0. So now, okay, so there's a copy of the standard model in our universe that has a small value of the Higgs mass squared. There are many other copies where it's large. This is just a manifestation of the fine tuning. So now the question you have to ask yourself is, why are we somehow the copy that has the small value of the Higgs mass squared and not one of the copies that has a large value of the Higgs mass squared? And the idea is to ask the question, what does it mean to be us? Right? What does it mean to have one of these copies of the standard model be the copy of the standard model that we see around us? What it means is that that copy of the standard model contains most of the energy density in the universe, right? So you can have lots of different copies of the standard model. If they're each in decoupled sectors, if only one of them has some large temperature, then of course that is the copy of the standard model that populates the universe, and we actually see when we look around us. So the question in naturalness is to arrange a mechanism by which you can imagine giving all of the energy density in the universe to this copy of the standard model, and less or no energy density to all of the other copies over which the Higgs mass squared parameter changes. Now, there's one other interesting effect. So we're imagining we have a large number of copies n of the standard model. There's one other interesting effect that we get when we have some large copies of the standard model, we have n large. So that's an interesting effect, which is just something you can think of as the renormalization of the Planck scale. So this is a fairly well-known result that you can imagine having n species of something. And of course, n species of something will run in loops that give wave function normalization to the graviton, right? So if I have n different copies of species, they all run in loops that give wave function normalization to the graviton. Then that large wave function normalization, of course, you know if you have a field where it has some fundamental scale, but then some renormalization effects give it a large wave function normalization. In terms of the canonically normalized field, the effective scale due to that wave function normalization will be very different. All right. So the consequence in a theory with n species is that actually, although you might think that the real scale of quantum gravity is m Planck, the gravitational sector actually grows strongly coupled, at the very least at some scale that is n, where that's the number of species, times some scale of gravitational strong coupling. Or in other words, in a universe with n species of something, the gravitational cutoff, where gravity grows strong and quantum gravity enters, is of order the Planck scale divided by the square root of n. So now having a large number of copies of the standard model does two things, right? It gives us a tail of a distribution wherein one of the copies, from statistics, the Higgs mass squared should be small, just from accidental cancellations. And it tells us that the cutoff associated with the gravitational sector is also being brought down by a factor of root n. Okay. So now you can imagine one of two possible scenarios. Well, you can imagine lots of different scenarios. But you could imagine one scenario in which you took 10 to the 16 copies of the standard model. So if you took 10 to the 16 copies of the standard model, of course, the scale of quantum gravity would come down to 10 to the 10 GeV. And you could have the effective scale of the cutoff in the Higgs sectors also be 10 to the 10 GeV and get one Higgs that was close to the weak scale, right? So that's one possibility, 10 to the 16 copies of the standard model. The other possibility is to be slightly less ambitious, is to say, I still like grand unification, let me still want quantum gravity to only become strong above the scale of unification. So let me take 10 to the 4 copies of the standard model. That brings the scale of quantum gravity down to about the gut scale. And it tells me that if I want to get a Higgs mass squared that's of order the weak scale, then I need the cutoff of the Higgs sector to be about 10 TeV. So maybe in each of these copies of the standard model, there's supersymmetry at 10 TeV as opposed to down right at the weak scale. Okay. So we still have yet to answer the question, right? We have these two interesting effects that come in as we have large numbers of copies of the standard model. We still have to answer the question, why is the universe filled with fluctuations of the particles of the copy that had the smallest Higgs mass? And this is where cosmology comes in. So cosmology came in for the relaxion in the form of inflation and the evolution of a field in the early universe. Cosmology comes in for naturalness in the form of the degree of freedom that reheats the early universe after inflation. So the idea is, imagine you have inflation in the early universe. Inflation ends. Of course, you have to reheat in order to restart the universe. And imagine all of the energy density of the universe at that point is stored in some field phi, which we'll call the relaxion. Okay? And reheating proceeds through this field phi, decaying into all of these different copies of the standard model. So the game that we have to play is to have phi decay preferentially into the copy with the smallest value of the Higgs mass. Now, we could just put that in by hand, but of course that would be a fine-tuning. So the philosophy is to imagine that at the level of dimensionless couplings, or the level possibly super-normalizable couplings, that phi couples universally to all of the different copies of the standard model. And in particular, the simplest example you could take was to have this field phi in your Lagrangian coupling through, again, some dimensionful parameter g, just having phi couple to the Higgs portal. Okay. So now, what we'd like, so now, of course, through all of these couplings, phi, which carries all of the energy density in the universe, will decay to all of these different sectors. And what we need is for the branching ratio for phi into the sector with the smallest value of the Higgs mass squared to be the largest branching ratio, right? If it's the largest branching ratio, the largest fraction of the energy density of phi goes into that copy of the standard model, and that explains why the universe is made mostly out of the particles of that copy and not of the other ones. All right. But the ingredients for that turn out to already be naturally built in. You just have to get lucky once. So the getting lucky once requirement is phi has to be lighter than the scales of the Higgses in all of the sectors, okay? So for each sector, of course, there's a distribution of Higgs mass squared. Each one has a different Higgs mass squared. The smallest one is this thing that's down by a factor of root n, at least statistically speaking. We need phi to be smaller than all of those scales. And the reason that's important is we need somehow for the decay of phi into these different sectors not to be proportional to the masses of the Higgs in each sector, but to be proportional to 1 over the masses of the Higgs in each sector, right? Because if the branching ratio of phi into each sector is proportional to inverse powers of the Higgs mass of each sector, then of course the largest branching ratio will be to the sector with the smallest Higgs mass. And to satisfy that requirement, this guy has to be lighter than, of course, all of the Higgses. Okay, now the details you can go ahead and work out. Of course, in all of these different sectors, if the Higgs masses scan from positive to negative values of the cutoff squared, at least half of the copies of the standard model don't break electroweak symmetry, right? The other half do. In the copies that break electroweak symmetry, the decay of the phi you can think of as going through mixing with the Higgs in that sector. So it typically wants to go through mixing with the Higgs, and then it will decay, for example, into whatever kinematically accessible fermions exist in that sector. So in phases where electroweak symmetry is broken, you get decays of this form. And these decays, because they go through mixing with the Higgs, the partial width into each sector goes like the Higgs VEV in that sector, which gives you this mixing term over the Higgs mass squared. That gets squared. So at the end of the day, these branching ratios end up being proportional to 1 over the Higgs mass squared in each sector. All right, so that's the sectors where the Higgs mass squared is negative, so there's a vacuum expectation value. In the sectors where it's positive, of course, you don't break electroweak symmetry. And so then you can just decay to massless gauge bosons, but you still have to do it through the Higgses. And so in those sectors, what happens is you decay through a diagram where you have a loop of Higgses, and then you go, for example, to any of the massless gauge bosons in that sector. So in these theories, where the Higgs doesn't get a VEV, your decays go through diagrams of this form, but you're still suppressed by the mass scale of the Higgs because it's running in the loop. Okay. So in these sectors, the partial width actually goes something like 1 over the Higgs mass squared squared. All right. So you get even more suppression in the sectors where you didn't break electroweak symmetry. So now you have this nice picture. What you had to assume was that the particle that decayed, the reheaton that restarted the universe, it could couple universally with the same coupling strength to all the different copies of the standard model. As long as it's lighter than the lightest weak scale in all of these sectors, then its decay into each sector will go like inverse powers of the Higgs mass squared in that sector. So there's a preference for the sector with the smallest Higgs mass squared, and there's a preference for the sector that breaks electroweak symmetry over its counterpart on the other side of mh squared equals 0 that didn't break electroweak symmetry, right? Because of these different powers of the scaling with the Higgs mass for the broken and the unbroken case. So this now gives you a preference for decaying into the sector that had the smallest Higgs mass squared that also turned out to be slightly negative. In other words, electroweak symmetry was broken. Therefore, this particle deposits most of its energy into that sector. It, of course, does deposit small amounts of energy into the other sectors. The energy density in each sector from the decay of this particle, so into the ith sector relative to the one that gets the standard model, this goes like, so the energy density in that sector relative to the standard model goes like the ratio of the decay widths. Of course, these things are going like squares of the masses, so that means the sectors with Higgs masses closest to ours get some reasonable fraction of the energy density, much smaller than ours, but still non-zero. And then the further you go away in scale from the standard model value of the weak scale, the less and less energy density you get. So that explains, in this theory, why the universe is filled with standard model particles that came from a theory where the Higgs mass squared is small. It was cosmological selection from the decay of a particle, and you just used kinematical properties to pick out the one that we know. Before I answer your question, there's just one other, what's the observable, of course, in this theory? Well, the observable is that you do end up with some energy density in each of these copies of the standard model. And that energy density, of course, if they're light particles, that means there are things like dark radiation. So there's contributions to the effective number of neutrinos that we can see in the early universe. And so these theories have very interesting predictions for N effective, which of course are currently bounded, but we would hope to make significant improvements in our measurement of in future CMB measurements like CMB stage 4. So this is cool because it really tells you to look in a completely different place for the solution to the hierarchy problem than you've ever looked before. It tells you to look for dark radiation, right, which is not something that anyone would have ever associated with the solution to the hierarchy problem, but here it is. Okay, questions? Whoa, okay. All right, someone back there had a question first? You're good? Okay, all right, then we can start. Yeah?
Why doesn't phi have a hierarchy problem?
Why doesn't phi have a hierarchy problem? So, good. Well, one possibility, so you could certainly imagine the cutoff of the phi sector is small, right? We don't know anything about the sector in which phi lives. The only thing that we had to specify was this supernormalizable coupling. This supernormalizable coupling could be small, right? Because the only thing that we really care about is the ratio of energy densities. We have specified that phi has a lot of energy, and its energy density sets the energy density of the universe. So we don't have to worry about having enough phis or having enough energy density in phis. We're just putting that in by hand. And then you could imagine phi is just living off on its own. It's sequestered from everything else. And at least the weak form of the hierarchy problem is not a problem. You could rerun the story. So I gave you the scalar version for simplicity. You can rerun the story with a fermion reheaton. It's also possible to have a fermion decay do it. And there, of course, you have no problem understanding why it's natural. So there's really not a hierarchy problem associated with the phi. The only thing that you have to understand is you had to get lucky and have this mass scale be smaller than Higgs mass scales. So I think Nima would say, this is like the mu problem in the MSSM. Why is the supersymmetric mass parameter smaller or of the same order as all the Cici breaking parameters? The same thing is sort of true here.
But it can be a lot lower in this case. No, it doesn't really matter.
Yeah, it doesn't really matter, right? Yeah.
Why should phi actually couple to the Higgs?
Well, because that's the natural portal interaction, right? I mean, you can ask yourself the question, we know the standard model has a bunch of accidental symmetries. We know that gauge invariance and Lorentz invariance only gives us a small number of portals that can be, renormalizable or supernormalizable interactions. And so in the case where the theory I have a phi, this is the leading interaction I can write down of any copy of the standard model. Okay, so it's the natural place to put it. It's not really a terrible assumption that this is the leading interaction.
Could you elaborate a little bit on the tuning issue of how to generate the 10 to the 16 and?
Sorry, how to generate it? Well, you could simply imagine there was a universe with a very large discrete symmetry, right? It seems uncomfortable, but it's.
In the paper, they have some mechanism like small parameter or whatever, I remember.
For generating many different copies, you could just have a large discrete symmetry. There are many ways to do that. That's not really a deep issue with this construction. Yeah, okay, you had a question?
There's also a limit on the reheat temperature of the thread. It can't be too high.
Yes. I mean, there are actually various limits on the parametrics. There's a relation between the reheat temperature and, of course, the partial widths of this particle. Here, this is just giving you the relative energy densities. But, of course, the games you need to play, you need to satisfy constraints on the size of the coupling. And so once you put all the degrees of freedom together, of course, there are constraints on the reheat temperature. There are also other constraints, okay? There are constraints on the fact that these sectors have to be factorized from each other, right? So in particular, what works about the scenario is the notion that these sectors are never in thermal equilibrium with each other. If there are any other interactions, so back to your question about why did phi couple to h squared, the real question you should ask is why does h squared not couple to some other h squared, right? Because if those couplings exist and they're not forbidden by any symmetries that exist at the level of this construction, then of course the various sectors can be in thermal equilibrium and then you're back to being in trouble. Okay. Yes?
In your formula for decay rates, I should put in different mass scales to make them dimensional.
Yes, of course. I'm just trying to give you the parametric. So typically it's all saturated by the mass of phi, right? Okay.
So you're assuming all the other mass scales are identical in different sectors?
No, there are obviously subtleties. So in sectors where I've broken electroweak symmetry, the masses of the fermions vary. If I'd assume the Yukawas were all the same, there will be sectors. But as I make those scales larger and larger, the only thing that happens is these modes turn off more and more, right? If I keep the dimensionless couplings fixed, that's really what enters this partial width. That doesn't matter. as I take into account the fact that more of these modes turn off kinematically, the story only gets better, right?
Also, since we have these different sectors, does it make sense to say, okay, now we populate different sectors and they could be a dark matter candidate as well?
Yeah, so there's an energy, so what is the issue? The issue is there are adjacent sectors with energy densities in them. You actually want the energy densities in those adjacent sectors to be smaller than ours, right? So dark matter would require them to be larger than ours. And of course, also in the simplest version, the adjacent ones that get comparable energy densities, all of the energy density goes into light states that don't necessarily make good dark matter candidates. But you could certainly imagine some picture in which it worked out. It's just in the simplest version, it doesn't seem to be, an automatic output. Yeah.
Could you remind me why the M5 has to be smaller than the MH?
It's because if it's larger, right, then this thing can just decay on shell to pairs of the Higgses. And that doesn't, so then there's no reason for you to understand, there's no suppression that goes like the mass scale in each sector, right? So when the Higgses get heavy enough, of course, some of them will be cut off, right? The heaviest Higgs sectors will be kinematically forbidden, but the branching ratios for every sector where you're kinematically allowed, until you start to squeeze the phase space, your branching ratios will not really depend on the mass scale, okay? So you have to go through an off-shell Higgs to force the decay rate to depend on inverse powers of the Higgs mass squared. So that's why that constraint is required. Yes?
Sorry if I missed that, but what is the explain the connection between the relaxation and inflation?
The reheaton? So we're talking about naturalness? You want to talk about the reheaton and naturalness or the relaxion? The relation, so I mean, the only constraint we're imposing is that there is uninflationary epoch where Hubble is less than lambda QCD that lasts for 10 to the 40 E foldings. In the original construction, the inflationary sector is assumed to be separate from the reheaton. It is, of course, possible to construct a theory in which the relaxion, in which the relaxion is both the relaxion and the inflaton. Well, this is the product of the Tel Aviv group, right? So I haven't read Tomer's paper. They have a couple papers now in the last couple months. I think the answer is positive. They certainly didn't write, the title of their paper is not, is the relaxion an inflaton? If that were the title, then of course you would infer by Hinchley's rule that the answer was no. Because that was not the title of their paper, I think it is likely that you can do it. Okay. In the original paper, they don't discuss it, but there have been follow-up papers discussing it. By the way, there is a paper from the Weizmann group, from Zohar and Gilad, asking the question about the compactness that is titled, is the relaxion an axion? And of course, they know about Hinchley's rule. Okay, other questions?
Are there any coupling at all between these different sectors?
No, so I mean, again, as we talked about, the thing that you have to assume is that they're actually factorized. And you could imagine sequestering them geometrically, right? Of course, we know in any actual sequestering scenario from string theory, there are still couplings that come from dilatons and other things. So then it's just a constraint. The couplings have to be small enough to not give efficient reheating or thermalization of two sectors with each other.
Follow that question is you think about cross coordinates for especially half of these couplings set model will have their own initial symmetry, right?
Yeah, you just have to forbid the cross cortex. Sorry, we're just assuming for simplicity the cross cortex are forbidden. Yeah, so that's this picture of geometric sequestration. You imagine they live on different branes. The different branes are only connected maybe by their coupling to phi, but that coupling phi can be made small enough not to introduce large radiative cross cortex. And then you imagine whatever stringy effects exist in your theory are also small.
But at the end of the day, the cross coordinates will be used by
The cross cortex will exist, but those are small enough to be negligible. Any other questions? Otherwise, I want to move on. Yeah? Oh, yeah, absolutely. But that's why the natural choices are either you solve the whole hierarchy problem with the number of species, where half of it's coming from reheating and probabilities in the Higgs potential, and half is coming from renormalization of the Planck scale. That's why 10 to the 16 was a good choice. The other choice of 10 to the 4 is just motivated by inflation, by gauge coupling unification. And then you imagine there's something like supersymmetry coming into the scale. But absolutely, I mean, the values of n, obviously, if you had n much larger than 10 to the 16, then of course, this mechanism would be gilding the lily. I should say, of course, as soon as you learn that there's a renormalization of the Planck scale from a large number of species, you should be tempted to solve the hierarchy problem with 10 to the 32 species. This, of course, was done a long time ago. You could call this thing the flat space holographic dual to large extra dimensions. The problem with that, with solving the hierarchy problem with 10 to the 32 copies of the standard model, is just that the cutoff of quantum gravity is right at the weak scale, so it's just another cutoff solution to the hierarchy problem. Okay. All right, so that's all I want to say about dynamical mechanisms. Hopefully the sense that you've gotten from this is that it's an interesting direction to pursue, right? The idea is to give up on notions of technical naturalness, to allow the cutoff to be large, not necessarily at the Planck scale, but somewhere above the weak scale, and to really be willing to pay that price, but then to have some mechanism, typically involving cosmology or vacuum selection in the early universe, that allows you to pick out a value of the weak scale that's small. And these are fun directions to pursue because the observables associated with them are not associated with producing particles at colliders, but rather are associated with things like cosmological observables that you could hope to see by looking at the sky. Okay. So there's a very nice relation, right? Every time you solve the hierarchy problem, you get some new observable, and the question is, what new observables haven't we thought of yet? Yes?
Could you make a comment on, in the relaxion and the naturalness, what is the most unsatisfactory feature of the models right now?
They're both brilliant ideas. The authors are all fabulous and handsome and beautiful and spectacular. The issue of the question of the relaxion is, there's several questions. There's how do you prevent yourself from just multiplying the tuning of the weak scale and the Cici? Like once you take the Cici into account, how do you not understand that there's just a larger number of vacua over which you have to scan to get the Cici right? So that's maybe the deepest challenge for the relaxion. The technical naturalist question is also there, although maybe something could be done to solve that. The inflationary question is there, but could potentially be solved. So that's maybe the hierarchy of questions you would want to grapple with for the relaxion. For n-naturalness and this Reheaton picture, there's nothing deeply problematic about the picture. You need to believe in a large number of species that inhabit the same universe, but it's not obvious that that's problematic. And you need to believe that there's a sequestration that prevents these sectors from talking to each other, but that also doesn't seem too problematic. It's a nice idea, and what's especially nice about it, right, is that it really has a robust prediction because you do have energy densities associated with your adjacent sectors. And so, this is a reason why those of you doing cosmology, or those of you who are down the hall from cosmologists, should go and cheer for them to do C and B stage 4. Okay. So now I want to take a sharp turn into rampant speculation for the last 10 minutes of my lecture. And I want to draw one more cartoon for solving the hierarchy problem. So the real, a simple way to say what the hierarchy problem is that in a Wilsonian effective field theory, there is no mixing between physics in the ultraviolet and physics in the infrared, right? If I define my theory in the ultraviolet, it knows nothing. It has a length scale, whatever the UV scale is. It knows nothing about physics in the far ultraviolet, in the far infrared, so it can't possibly generate a scale that is at much larger scales than the scales that it knows about, right? That's the whole, the essence of the hierarchy problem is we have a fundamental scale, we have no way of knowing about a much smaller scale because there is no connection between the far UV of the theory and the far IR. So now you can say, okay, great, that's the problem. Let me fix the problem by mixing the UV and the IR. So let me instead draw a cartoon where the UV and the IR are connected in some way. Okay. So the first thing you would say is that's completely insane, right? It is certainly a violation of Wilsonian effective field theory, but it's also just very hard to imagine how it works. Thankfully, we have examples of UV-IR mixing. So the classic example of UV-IR mixing is just in a theory of quantum gravity. So the simple way you could explain it to yourself is, of course, you take two protons, you accelerate them to Planckian energies. You smash them into each other in a very small piece of space, and of course, you'll make a microscopic black hole. So now you say, great, I want to probe further into the UV of my theory of quantum gravity. I'm going to take protons, smash them together at even higher energies, and I should get even further into the UV of my theory of quantum gravity. So you do that, and you find you make a bigger black hole. Okay, right? But a bigger black hole is probing larger length scales of the theory. It's probing the infrared of your theory of quantum gravity. Right? The more energy you stick in there, the more you try to go to the UV, the more you learn about the theory in infrared. Okay, so that's a simple toy story you tell yourself about UV-IR mixing. There's a deeper and more robust version that we see in string theory, which is associated with the notion of T-duality. So of course, you can have a theory of strings compactified on a circle of radius r. T-duality tells you that that theory is equivalent to a similar theory of strings on a circle of radius 1 over r. And so now you can imagine saying, if I took my first theory, and I wanted to take that radius smaller and smaller to probe the UV of my theory, but I know that's equivalent by T-duality to a larger and larger radius circle, so I'm actually probing the infrared when I try to probe the UV. Okay. So we know of examples, they're beautiful, they're incredible, they have to do with some of the deep mysteries of quantum gravity, where there is actually mixing between the short range and long range degrees of freedom in our theory. Now, quantum gravity is scary, and if we just had to rely on a notion that this existed in quantum gravity, that wouldn't be very satisfying. We wouldn't necessarily know how to make too much progress. So what you should do instead is you should look for phenomena of UV-IR mixing in quantum field theories, all right? And ask, if I can construct a quantum field theory with UV-IR mixing, what can I learn about that, and can I use that as a way to have a constructive framework for studying a breakdown of Wilsonian effective field theory and trying to understand the hierarchy problem. So thankfully, we have an example of UV-IR mixing in a quantum field theory. This originates, well, it has a long history. It really sort of originates with Heisenberg, but in the concrete framework where we can do something with it, it starts with Nadi Seiberg and Edward Witten. And the particular example in the quantum field theory was by Seiberg, Mark van Ramsdonk, and Shiraz Minwalla, and this was around 1999. So what they were interested in, motivated by a string construction that Nati and Edward made, was actually considering field theory on non-commutative spacetime. So you can imagine your theory actually has a non-vanishing commutator between spacetime coordinates that's proportional to some real anti-symmetric tensor with some constant values in it. Okay, so this tells you this is a theory with spacetime non-commutativity. This theory is also a theory with Lorentz violation. And for as far as we'll talk about things, we should also just think about this as being a Euclidean theory rather than a Lorentzian signature theory. But okay, so you now ask yourself, if this is my theory, I have some space-time non-commutativity, what can I do? Well, this is a somewhat complicated theory to study, but it turns out that you can take, if you have a space of functions on this theory in the space-time, that you can instead study it in terms of fields constructed on a normal spacetime, a commutative spacetime, but with a non-commutative product. So field theory on this non-commutative background, you can equivalently study by constructing a star product. You'd think I'd be better at drawing stars. My daughter is 18 months old. She makes me draw them all the time, but there you go. Okay, so star product. If you have two fields, you want to bring them together to the same spacetime point. That's associated with some star product of those two fields that has some extra factor associated with it that's proportional to this non-commutativity parameter, and then some appropriately constructed derivatives. Okay, so instead of working the theory with non-commutative spacetime, you can work in the theory with commutative spacetime and this non-commutative star product, where the non-commutativity is associated with this funny exponential factor. So now you can go ahead and you can take any of your normal favorite commutative field theories, and you can construct non-commutative versions, where you take normal products of theories, products of fields at the same point, and you replace it with the appropriately defined star product. And now you can ask what happens. So as far as we're concerned, I just want to study a very simple example, which is the non-commutative version of phi to the fourth theory. So the action for this theory in 4 dimensions, it just starts looking like the usual one. So amusingly, actually, the quadratic portion of the action just looks like a normal commutative action. And the reason for that is that integrated over d4x, the non-commutativity associated with the star product of just two fields just turns into phase factors and total derivatives that drop out that are irrelevant for the action. So at least the quadratic part of the action looks like a normal commutative field theory. And then we have evidence of non-commutativity coming from what the appropriate non-commutative generalization of the phi to the fourth interaction. Okay, so what does that buy you? All right, well, we can go ahead and we can compute loops in this theory. Now, we know if we have a normal commutative phi to the fourth theory, this is a theory with a mass gap, right? We have some mass term, and we know there's going to be ultraviolet divergences. So if we do integrals up to some cutoff, then of course we know diagrams associated with this phi to the fourth interaction will be quadratically divergent. So now we can ask ourselves what happens in this case. So the non-commutativity does something interesting. All right, if you look at what it means, you define the star product. It has this extra phase factor that picks up momenta of the various lines that come into an interaction. And so that means to construct the Feynman rules for this theory, you construct them like you do normally, but you pick up a bunch of different phase factors, exponential phase factors in momentum space that just correspond to these exponentials contracted around that non-commutativity parameter. And that dresses all of the Feynman diagrams. Now, something else happens that's interesting, okay? So when you construct these interactions, so in a normal commutative quantum field theory, we're used to, if we write down a vertex and we write down the external lines, we can cross them around the vertex without any cost to connect them to the external states. But in the non-commutative case, if we do that, the factors that are associated with this exponential start to actually pick up extra phase factors. And so we have to differentiate diagrams where we just immediately connect lines from a vertex with the external states without permuting them across each other. We have to distinguish that from ones where we do actually think of moving a leg across each other. So the simplest way to see where that might happen is just to compute one-loop diagrams. So, of course, we know in the normal commutative phi to the fourth theory, there's a one-loop diagram that just looks like this. Now, that diagram, of course, also exists in our non-commutative theory. And so this we would call a planar diagram. But there's also a diagram where instead of, if these were my two external states, and I took these two lines and squeezed them into a loop, if instead of that, I took this line and took it to the external state, and I took this line and made it into a loop, then that would correspond to a crossing, and I would pick up an extra phase factor. And so I should distinguish these planar diagrams where I didn't cross any lines from non-planar diagrams where I do cross lines to connect to the external states. So in addition, I should think of there being a diagram where to get to the external state, I crossed. Okay, so now there's an extra phase factor associated with that crossing. All right, and that phase factor in particular involves, because of the way the star product is constructed, that involves one of the momenta that's running through the loop. All right. So now we can go ahead and we can compute these two diagrams, okay? So the planar diagram, the first one, this goes like the coupling, there's a factor of 3, there's the normal integral d4k over 2 pi to the fourth, and then there's the normal 1 over k squared plus m squared. So we already know this is d4k over k squared. This thing will give us a quadratic divergence that we're familiar with from commutative phi to the fourth theory. And then the non-planar diagram, right? The non-planar diagram has a slightly different combinatoric factor, still d4k over 2 pi to the fourth. And now it has an extra phase factor where I'm writing it just for simplicity as k cross p, but really this is just shorthand for taking that exponential and transforming it to momentum space. So one of the derivatives picked up an internal momentum p, and the other one picked up an external momentum k. Okay, so there's an extra exponential phase factor associated with the non-commutativity of the theory. And now you should start to think that something is interesting, right? We know these integrals are just going to give us quadratic divergences, but this now has some interesting oscillatory piece. And it's not obvious that it's going to behave in the same way. So we can go ahead and we can take these integrals. We can act like a Wilsonian effective field theorist, so they're divergent. We can just integrate them up to some cutoff lambda. it's convenient because of the way the integrals behave to do it with a smooth exponential cutoff parametrization. We can go ahead and do that, and we can evaluate the integrals. So for convenience, I'm going to skip to the answer. So integrating up to some cutoff, the planar diagram gives us what we already know and love. So it gives us a quadratic divergence, right? There's a quadratic divergent piece. Then there's a logarithm. And then there's finite stuff. All right, nothing scary about that. We can evaluate the non-planar piece, and the non-planar piece now is different because of this oscillatory exponential factor. The non-planar diagram depends on something that I'll call lambda effective. It looks the same, it shows up in the same way. But this lambda effective is actually a funny combination of the original cutoff. So lambda effective is 1 over the original cutoff squared plus some object that is involves this non-commutativity parameter and the external momenta. Okay? So this all has the right dimensions of mass if you go ahead and track the dimensions starting from my definition of the non-commutativity parameter. And it appears in the same way as the UV divergences from the planar diagrams. But now we can go ahead and study what this does. So we can go ahead and study these diagrams. We can take the cutoff to infinity. So that sets the effective parameter appearing in the non-planar diagrams just to be equal to this. And now we can go to the infrared of the theory. So we can take the external momenta p to 0, right? So now we're probing the infrared of the theory. But now when we take p goes to 0, now this parameter blows up, right? So the non-planar diagram is giving us an infrared divergence. This is a theory, right? The commutative version of the theory has a mass gap and a UV divergence. There's still a mass gap and a UV divergence that's reproduced in the planar sector of the non-commutative theory. But there's also an infrared divergence, which we know signals the existence of massless particles. Okay, so that's amazing, right? That's a theory where in our normal formulation of a commutative quantum field theory, we think of this as UV sensitivity. A deformation of the quantum field theory tells us we now get something that looks like some evidence for physics in the infrared. It gets even more cool, so you could ask, okay, what do I do with this, right? If I'm a Wilsonian effective field theorist, I try to give up because I don't know how to construct some sort of consistent Wilsonian effective field theory, right? Wilsonian effective field theory is predicated on the notion that I can coarse grain as I go to the infrared of the theory, and I can't do that here because there's a connection between the ultraviolet and the infrared of the theory. But if I'm a Wilsonian, I could do something else. If I was a Wilsonian, I would say, well, I look at this infrared divergence, all right? That's something that shows up in observables that I associate with my quantum field theory. So what are particles really but things that we see evidence for in the behaviors of correlation functions and other observables? So if I see an infrared divergence showing up in some correlation function, I could then interpret it as the existence of a new light particle, and I could try to write down a Lagrangian for it. So in particular, I can take this infrared divergence, I can write it down as a new particle in addition to my original particle that I defined in my fundamental theory. That new particle, I would give a contribution to the action. It would have a kinetic term that was funny. So instead of being contracted with the metric tensor, it's actually contracted with the non-commutativity parameter, the square of the non-commutativity parameter. It also has to have some funny extra term that's higher derivative in order to effectively and correctly reproduce the form of the infrared divergence. All right, and then because it appears in these non-planar diagrams where phi to the fourth, these phi particles are the external particles, there then has to be some coupling. In particular, there's an effective mixing between this new particle chi and the particle phi. Okay, so if I were Wilsonian, right, I would look at this theory in nature, I would see infrared divergences, I would interpret them as the existence of a light degree of freedom. I would write down a Lagrangian for that light degree of freedom. It would look a little peculiar to me, but in particular, it would be a massless scalar, and I would have no ability from my Wilsonian perspective to understand why it was light. But of course, knowing what the full theory is, right, it's not mysterious. It's just an infrared divergence that's a consequence of the UV-IR mixing that's intrinsic to a non-commutative quantum field theory. So what is the lesson from this? Okay, the lesson is not that this particular construction solves the hierarchy problem, right? If this were a solution to the hierarchy problem, you would interpret this IR divergence as something like the Higgs, but this really doesn't look like a Higgs, right? In particular, this is just a Euclidean construction. This object is not some propagating degree of freedom that looks like a normal scalar in Lorentzian spacetime. Okay, so this alone is not solving the hierarchy problem, but it's giving us a hint of something that we can try to do to really open up an entire new front in solving the hierarchy problem, right? If we can identify systematically classes of quantum field theories or extensions of quantum field theories that exhibit controlled UV-IR mixing, then we would have a playground in which we could understand the emergence of what look like light propagating degrees of freedom from a theory that in fact is dominated by physics in the ultraviolet. So the fact that this phenomena arises in string theory, the fact that it arises in some very interesting field theories, this is a sign that this is an interesting place to look. The fact that the theories that we have now, this particular non-commutative quantum field theory, doesn't exactly work, doesn't tell us to give up. We only know about this example because Seiberg and Witten were just playing around with interesting string theories. And then Seiberg and Minwalla and Van Ramsdonk decided to study it in more detail. So a systematic effort to understand how UV-IR mixing might work and how it might be applied to physics of the Standard Model, that's something that no one has ever attempted. But if you want to do something, if you're tired of the old solutions, or if you're not satisfied by the new classes of solutions we have so far, and you want to know where is a deep place, right? Where is something that requires a real expansion of our thinking about quantum field theory, if the solution to the hierarchy problem was really something profound and not just some extra set of symmetries, I would suggest that this is a fun place to look. Okay, so this is certainly some place where I plan on spending some more of my time. If you have more questions about how this specific example works, I suggest you talk to my student Seth. Seth has taught me a lot about some of the subtleties at play here. But more generally, this is something we should spend more time on in the future. Okay, there were lots of things I didn't have time for. I didn't have time to talk about conformal symmetry solutions to the hierarchy problem, which are subtle but interesting. I didn't have time to talk about Anderson localization as a solution to the hierarchy problem. There are lots of other solutions to the hierarchy problem. We can save many of those for the discussion section. Hopefully what I've conveyed to you is that it is a very exciting time to be coming into theoretical physics, because instead of being someone who, when I was a student and I came into the field, I had to learn intricacy about supersymmetric model building because that was the expectation of how the universe was going to work. We're pretty sure that's not how the universe is working. And so that means we're close to a paradigm shift, right? We actually have to give up our old ideas and we have to go look for new ones. And you guys are the ones who get to look for the new ones. So you get to think big, and you get to not be afraid to think big, and it's been fun to at least give you an invitation to do that. So thank you very much for your time.